So this week we are doing electromagnetic induction. Electromagnetic induction is what we use to describe the interaction between changing magnetic fields and electric fields. So if you have a changing magnetic field, it will produce an electric field. That electric field could then interact with things. Let's say if you had a conductor such as this coil of wire, then the conductor by definition means we have charges that are free to move about. So typically we would be talking about the valence electrons. They would be free to move through this. If we create a circuit with this conductor, then the changing magnetic field would then cause a changing electric field, thus making these charges move due to the electromagnetic or Coulomb force. And we would thus see a current. So we're going to see that today. We're going to apply, try to learn a little bit about these topics, talk about a couple of things such as Lenz's law that you may or may not have heard about in class. So we have several pieces of equipment here today, and this is because we're going to start out with a permanent magnet to cause some of the phenomena that we see. Then we're going to move to using an electromagnet. We're going to do step 2 will be an electromagnet using the DC power supply, or what they call the lab jacks in the lab manual. And then finally, as the third step, we're going to move to an AC transformer and use that to produce the same phenomena here. And I'll also talk a little bit about some of the applications of this in everyday life. The very first one will be permanent magnet induction. All right, so they ask us to connect one of the coils in series. So these are one of the coils. These are also referred to in the lab manual as solenoids. Anytime you have you see this copper color. So coil of wire that is wrapped around, and perhaps you can see it here that it starts at this point and then wraps its way around this coil until eventually it ends up here. And so it's wrapped its way all the way around, in this direction, until it comes up over on this side. Okay, so that's slightly important later. We'll talk a little bit about how the implications of that. So these are called solenoids sometimes, and but also just simply a coil of wire is fine to refer to that. So we're going to take one of the coils, and they'd like us to connect that in series with the galvanometer. A galvanometer is new. You have used a multimeter before. A galvanometer is going to be able to measure current, as you might guess by the microamp measurement here. Galvanometer is unique in that it's mechanical here, that we're going to be able to see current moving, like the rate at which it changes, as opposed to just a digital number. This will give us an idea physically of what's happening, and give us some idea of the magnitude of the current that we're producing. So that's its job, is to give us a different visual representation of current that you've seen before. Okay, so I'm going to move some of these items out of the way here for us for a moment, and I'm going to take one of the coils and I'm going to connect it in series. So I'll take one of the wires here and connect it to the coil like so. Take another wire and connect it here. Okay, so at this point I have a series circuit for the galvanometer with the coil. So once we've done that, we're going to hold the coil still against the magnet. In other words, take this permanent magnet that's marked north and south, and we're simply just going to take, let's say, the north end, and we're just going to hold it still against the side of the coil. And do we see this particular, the hand move on here? And we do not. It is at 0, and it is not moving. So we do not see any electricity flow in the wires. And again, remember, if electricity is flowing, that's another way of saying current. That means the charges are moving. We would see something other than a 0 value here if that was the case. So now it says, with the magnet fixed, move the coil slowly so the magnet passes through the coil, and withdraw the coil slowly. Repeat with a more rapid motion. Is there a current in the wires? Okay, so if I take this and hold this still, keep an eye as I move this back and forth, you may see that, oh look, now we see that the hand on the galvanometer is moving, thus indicating we're getting a current. Okay, if I do this quicker, we'll see that of course it changes faster. You'll notice that as I move in this direction, we see it moves to the right. As I pull away, it goes to the left. it also asks us to repeat this with the poles reversed. In other words, if this is the north side, so notice when I go in, it moves to the right, and when I pull away, it goes towards the left. Let's take and reverse it so the south is on this side. If I move towards it, it goes to the left first, and then moves away to the right, okay? Now, I'm going to do the same thing. Let's put the north back face towards the coil, and they simply ask us with the coil fixed to move the magnet in and out. And of course, we see the same thing here. And so in other words, I go in, it goes to the right. When I come out, it goes to the left. And then if I put the south end going in first, we get the opposite effect there, okay? So they ask us to explain this a bit. It depends on what you've talked about in class. One of the things that you may have discussed is if you were to have a wire, let's say I had a current going through this wire, and let's say the current was moving, if we define that to be the direction a positive charge would move, I would use my right hand rule, which would be my thumb going up in this direction, and my fingers would curl around. So if I had a current moving in this direction, so if this was positive and this was negative and I have the charges moving in this direction, I would then see a current going like so, and the magnetic field would circle around this in this direction here, okay? If I am looking at a magnet that is entering in the lab manual, they give you a definition of what happens with the induced current. So they don't necessarily specifically mention Lenz's law, but Lenz's law is essentially, all it says is that if I change the magnetic flux, in other words, if I change the magnetic field that's going into this here, it would like to stay in its state that it's already exists in. So in other words, that means if I am trying to increase the magnetic field going into the coil in this direction, this will induce a current in this coil such that it will try to oppose the change that occurs. So that's important. It doesn't always mean that it's always going to be opposite of the direction of the magnetic field that's going in, but it will have an effect, okay? So one thing I should probably point out here in terms of the magnetic field, if I have a bar magnet like so with north and south, magnetic field lines are used to represent the direction that charged particles would move, or a direction they could move. We always define the magnetic field to be going away from the north end and into the south end. So this is just the convention. Okay? Magnetic field lines, if I draw them so that we're bunched together closer here and maybe spaced out further here, that means the magnetic field would be stronger in this region than it is, say, out in this region here. Okay? So also, just to point out here, the magnetic field does not stop. It does actually move completely through the material, all the way through that bar magnet, like so. So based on this idea, if I have the north end over here, that means the magnetic field is pointing in this direction. Right now, there is no magnetic field inside of this coil. I'm going to take this and move it in this direction so that the magnetic field in this direction will be increasing in this direction. We're going from no magnetic field to some magnetic field. So I'm increasing it in this direction when I put the bar magnet in. When that occurs, this is going to try to create a magnetic field to oppose that change. If I look at the wires that are here, in other words, just think about one of the wires. There's many of them up here in a row, but just one of these wires here. If I were to try to oppose this, which would be an increase in the field this way, that means I would like to have this guy create a magnetic field that's in this direction. So how do I do that? Well, let's go back to thinking about earlier when I said a current going like so, it would have the magnetic field. I would like a magnetic field from, pick this one piece of wire to focus on, the top part. I would like it to point back down in this direction to counteract the increase in the field here. In order for that to happen, that means my current needs to be moving in this direction, okay? Now, if I were to look over at the bottom side of this, I would still want it to in this direction, going down inside of the solenoid in this direction here to my right, your left. then that would mean that I would have to have the current flowing like so. Well, because this is wrapped in a coil, that's no problem. So in other words, I need the current to flow around in this direction, right, in order to make that happen. What we want you to focus on at the moment is the basics, and that is we have a changing magnetic field. So in other words, I can take this and place it inside, and notice that on my way in, we see current. But once I leave it here, there's still a magnetic field inside this, but it is no longer changing. Because it's not changing, my current is 0. So I have to have a changing field to induce an electric field that would then cause the current to flow. Okay? So change the magnetic field by pulling it out, I would then be decreasing. So at that point, when it's inside, I have magnetic field in this direction. When I pull it out, I would be decreasing the field that's in that direction. So here's where it gets a little tricky to think about. If I am decreasing the field in this direction, then that means this guy, because once we're here and everything is settled down and it's back to equilibrium, even though the magnetic field is here, there is no current anymore. But now that I'm changing things by pulling the field out, this will try to reach an equilibrium again. Well, how is it going to do that? In this case, since I'm decreasing the field over here, it wants to increase it in this direction. So now I have the field from this decreasing. It's still in this direction because north is still pointed this way. But this guy will now need to create a field that will be in this direction. So I'll have to use my right-hand rule again, but that means that the current would need to go around in this direction. When I pull this out, I'm decreasing the field, but it is in this direction. But it's because it's a decrease in the field, this wants to increase the field in that direction to maintain what it had just before I made the change. Okay? So let's turn it around, and let's now say that this is the south end. Okay? If I want to place the south end and move that in, at this point the field is in this direction. And in order for this guy, let's say at first I have no field inside, I'm going to put it inside. That means I'm increasing the field in this direction. So it is going to try to increase or create a magnetic field that goes in the opposite direction in that case, simply because it is trying to counteract the change. The change would be increasing this way, so it's going to try to decrease that by producing a field in the opposite direction. Okay? Left. If I pull this guy back out, once this is in equilibrium, I now have a magnetic field inside like we did before. However, this time it's going to be pointing this way because my north is now over here and the south is here. When I pull this out, that means I'm going to be decreasing the field that is in this direction. So in that case, the coil is going to try to produce a field that is in the same direction as that to try to counteract the decrease in the field. Okay, so it's always dependent on the change of the field, not necessarily just strictly the direction. It's not always going to be opposite of the direction. It's going to be opposite of the change. It's going to try to oppose the change. Okay? So that gets us through all three steps A, B, and C there in step number 1. Okay? So we took the north end, let's say, and brought it in. We pulled it out, we saw the opposite changes there, or if I did the south end, we saw the opposite of the starting point going in and then coming back out, okay? And then I could also move this relative to that. Either way was produce the same results. We're going to move on to step number 2. Step number 2 is electromagnetic induction. And again, this, instead of a permanent magnet, we're going to take this and replace it with this, because a moment ago, this gets a little confusing because a moment ago we were talking about taking a permanent magnet and creating a current here. But we also learned that because I'm creating a current here, this is producing its own magnetic field, right? So let's set this to the side for just a moment because we're going to come back and use that again. And what I'm going to do now is I'm going to take wires and connect to my DC power supply and run current through this coil. Okay? When I do that, it is going to create a magnetic field. Now, if I were to run it such that my positive was on this end, looking here, the coil starts to go around and goes in this direction. Okay? Then, looking at the other end, we'll see that it comes back over to this side here. So current would go looping around in this direction and end up over here, okay? If I was going to flow, make the positive here, I would have it coiling like this. That means on the top it would be going in this direction. So if I make this my positive, it would be flowing across the top in this direction, which means my north pole would be on this end. Whereas if I run it in the opposite direction, so that the current goes like this, so on top it is in that direction, I would put my thumb this way for the current, and then my fingers would coil in here to point the direction of the magnetic field down this way. So that would create the north pole here. So if I make this positive, I'll have a north pole on this side. If I make this positive, the north pole would be on this side for this particular one, okay? Now, to do that, instead of just connecting up directly, one way to do it would be simply to take two wires, plug it into our DC power supply and plug it in, but that's going to leave us with a permanent with the magnet turned on all the time in the same direction. So I'm going to use this switch, okay? This switch allows me to connect something to the center post here, okay? And when I put the switch this way, it's going to connect this post to this, and then also at the same time we'll connect this post to this, all right? If I switch it this direction, it will connect this post here, and on this side it will connect this post here. It will not connect this side to this side, okay? So I'll let you think about that a little bit as you see this. So what I'm going to do is I'm going to connect the center post to this coil, because and then I'm going to take this set of posts and connect to my power supply, and I'm going to take this set of posts and connect to my power supply. The only difference is I'm going to reverse the polarity. So in other words, I'll make one of these posts positive and one negative, and then on this side I'll switch that so it's positive negative. So that way when I go in this direction, I could have positive going in one direction through the coil. So let's say, for example, if I had positive down here, I would then make one side of this coil be positive, and then if I switch this way, I might make this side be positive. Okay, so we'll look at that as we go along. So I'm going to take two wires here, and plug the red one in. I'm going to put it on this side. I'm going to take the purple one and place on this side. Okay? So at this point, I'm going to try to match these up here so that this side is the same as this, this is the same as that. All right? Now, let's take my power supply. I'm going to connect my ground here. And then I'm going to take positive and connect here. And I have this set for 5 volts. All right? Now, if I connect this up like at this point, I have now made a connection between the yellow wire and the red wire. And I've also made a connection between the blue wire and the purple wire. The way that works is that the yellow wire would be the positive, so current would be flowing in this direction. It would come through here and connect here, go down this piece of copper metal, and then work its way back over to this side. So you can visually see what is happening here. Current's flowing in here, going down and across. Okay? I would like to be able to switch this the other direction so that this would now become, instead of this side being positive, I would like to make this side positive. So the couple ways I could do that. I could connect these directly back to here, or, because I've got a couple of shorter wires, I am going to simply do this, right? So at this point, this is what the complicated figure 7.3 in the manual there, where it shows the electromagnetic circuit. This is what they're trying to describe is this particular setup here, okay? Okay, once we have this wired up, what I'm going to do is if I give it current in one direction, we'll see that this deflects over to the left, and then I'm leaving the current on, so I now have a magnetic field set up here, and there is a magnetic field inside this, but it's not changing. But once I turn this off, it's going to go from having a magnetic field inside this to not having a magnetic field, which means you're going to see this produce a current, but then it goes back to 0 because now everything's back to equilibrium again. In this case, no magnetic field. All right? If I go in the opposite direction, we'll see it go to the right at first. And then when I decrease, we'll see, when I take it away, we'll see it go back to the left. Just like we saw earlier, when I did opposite poles of the permanent magnet, when we brought this in and out, depending on which end we brought in first, would cause this to go in a different direction. So it's all down to the Lenz's law. If we're increasing the field this way or decreasing it in that direction or vice versa, then this will try to compensate, producing a magnetic field to counteract that change. Okay? The only other thing they ask us to do here, so that was to connect one of the coils. By the way, I skipped over this a moment ago and didn't mention what they were calling these. They're going to say connect one of the coils called the primary to the lab jacks. So in other words, this is the primary that they refer to. It is the one that we have connected through all of this, but effectively goes back to what they call the lab jacks here. In other words, the power supply. Okay? So this is called the primary, and they're going to call this the secondary. They're introducing those terms because those are terms used in the construction of a transformer. And a transformer's job is to either, generally is to take a high voltage down to a low, or you can also transform a low voltage to a high voltage. And they do that by ways of interacting coils through these interacting fields similar to what we're seeing here. So they said to keep this one connected to the galvanometer, this is going to be connected to the lab jacks or to the DC power supply. So primary, secondary, galvanometer. Place the coils next to one another along a common axis like we've done here. And then we're going to start current in the primary, stop current in the primary. So we did that, we stopped it, and we noticed that when I started it, I saw it go in one direction. When I stopped it, it goes in the other direction. Again, all this is going to depend on how these would be wired if you were performing the lab. So the actual directions of what's happening here in terms of counterclockwise or clockwise and so on, it would be impossible for you to state easily without performing the full experiment yourself. But again, we're just trying to get the idea that we need a changing field. So then they ask us to do the opposite direction for current, and of course we see the opposite happen once we put it on and take it off, and that's the main thing, is seeing that we have direction changes cause that. Current direction changes cause this to behave differently. So they want us to repeat the exercises again with an iron core inserted. Okay, so an iron core is an easily magnetized material. This is not magnetized, although they can become easily magnetized, so it might have slight bit, but assume it's not magnetized, and that all of these, the typical way I like to think about it is that all of these atoms here all have what we call a magnetic moment. In other words, think about them as having like their own little tiny magnets, and they're all randomly oriented. So the effect is for every one you have oriented, say in this direction with my finger pointing direction of north, you would have one point of north this way. So the effect is they cancel each other out. However, because this is an easily magnetized material, meaning that once I apply an external magnetic field, then these molecules will line up in that direction of the magnetic field. So then all of their tiny little magnetic fields will add up with the external one you've produced to then create a total magnetic field here that would be greater than what it would have been without the iron core. So the idea here is that if I put this inside, and now watch the magnitude, in other words, how far this needle jumps. It pegged, it went actually off the scale in both directions. Okay, so let's go in one direction. We see it went to the right, come off, it goes to the left. We're going to go back to the right, back to the left to go in the opposite direction, turn it off, and we'll see it go back to the right here in the opposite. Okay, so same thing occurs. All right. So finally, what they want us to do then is move from the DC, which is this setup here, okay? So what I'm going to do in this case is I'm going to unplug the positive here for safety. I'm going to unplug these two wires. And I now am going to connect this guy to what's known as an AC transformer. In other words, I could take this and plug it directly into a wall socket, which is AC. It's alternating current. Okay, so when I refer to DC, that's direct current. That means if I turn on the current to this guy using this setup, we saw the current go in one direction and it maintained that same direction. So positive and negative were always in the same orientation, all right? Unless I reversed it on purpose using the switch. Imagine if I could take this switch and go back and forth 60 times a second, okay? Changing my direction 60 times a second. That is what our AC power supplies or AC signal would do coming from the wall socket. Okay, so energy from the power company in the United States operates at what we call 60 hertz, which means 60 times a second it changes direction. Okay, so what I'm going to use here is a simple AC transformer. This little transformer is not going to produce the signal. Okay, the effects we're going to see would be exactly the same if I plug this into the wall socket. But I'm not going to do that because that would be rather dangerous to have 110 to 120 volts here act live at this point. So instead, I'm just going to use this as more of a safety net. So this doesn't produce the effect. It's just simply going to take the voltage of 110 and step it down to somewhere in the region of about 8 volts. So I'm going to plug this into the socket behind me. And they're asking you in step 3, they say connect the secondary in series with an AC milliamp meter. I'll do that in a moment. And it also says do not use the galvan. We'll come back to that in a second. So I'm kind of doing C. I'm saying energize the primary with output from a 6-volt AC transformer. Okay, so these are in somewhere in the region of 6 to 8 volts. So by energizing it, they simply mean we're going to connect these two. And at this point, even though you don't see evidence of it, I have current running back and forth in this loop, clockwise, counterclockwise, depending on which way you're looking at it, but you're going to circulate current through here. In other words, I'm going to be making one side positive, one side negative, and then it'll flip, and the other side will become positive and the other side negative. And this will be happening 60 hertz, 60 times a second. So your magnetic field is going to be the effect of having a north-south pole magnet like this switching back and forth 60 times a second. Or, in the case of doing the electromagnet with DC, it would be the same as me switching this back and forth 60 times a second. So, based on that, what would we expect to see this guy do? Well, we would expect to see him swing back and forth every time this current changes direction. But it's going to happen 60 times a second. It's actually more than this can handle. I am going to do this very quickly just so that you can kind of see the effect. I do not want to do it long because I run the risk of breaking this because mechanically it can't keep up. Also, the amplitude will not be near as high because it doesn't actually have enough time to physically move from one end to the other. Okay, so you're just going to see it vibrate back and forth slowly. I'm going to try to get it on a camera angle and see if we can see that happen. Okay, right now we see it vibrating very, very, very quickly. And so, for example, if I pull this out, we see that right now this is when it's not moving. Now it is, it's vibrating back and forth quickly. Okay, all right, so I'm going to disconnect that because I don't want to damage this. So it asks you, so I went against what the lab manual says, so don't try this at home. I'm going to now take these and connect them up to our ammeter. And this time, instead of using, so ammeter, we know we're going to use current, so we're using common like we always do. We're also going to use, I'm going to go ahead and just put it in the milliamp side so we can get more decimal places here. So we're going to read off in milliamps on the scale. And this time, I'm going to change it. We still have to change it to current, so in other words a capital A, but I'm going to use this one that has the sine wave look on top, okay? So this means AC, whereas the straight and dashed line means DC. So we're going to notice now, I'm going to leave the iron bar out for a moment. And when I place these up together, I see that I'm reading 50 milliamps. And if I pull them apart, we see that that number gets smaller. Bringing them closer together, the number gets larger. Now, if I insert this, just like we saw before, we're going to expect that number to get larger. I'm going to put it somewhere in the middle, and we see now that we're getting 228 milliamps. Okay, 228.2, 0.1, somewhere in there. So as I pull this apart, of course, we would see it get smaller. Okay. Now, the way the meter works, by the way, is it averages this sine, because it's going to be sinusoidal, so it averages it. By the way, if you were to average a standard sine wave, you have as much above positive as you do negative, so if you averaged it, you would get 0. But if you square the sine wave first, then that would make all the negative values positive. Then you could take the mean to get an average value. But you've squared it, so you've squared all the values. So then you would take the square root to undo that original square that you had to do to make everything positive. So they call this root mean square, and that's the way you would average out a sinusoidal type of wave. So that's the way they do it. Sometimes you see that listed on meters as RMS. Okay, that covers everything on the steps of the lab manual. The one last thing I want to point out is the use for these devices. So if we were to talk about a, I'm just going to switch this back over to the galvanometer quickly just so we can see what's happening here. Okay, so imagine if I have a changing magnetic field. It doesn't matter if I produce that by running current through a coil in order to produce an electromagnet, or if I use a permanent magnet. And you can also use your imagination that I could maybe have some different geometries here. But the basic idea is if I take a changing magnetic field and some bundle of wires here so that I could either spin the wire or the magnetic field. Typically you're going to be spinning the wire. You'll do some kind of a spherical geometry in a lot of cases. So, but take this same idea and let's put a propeller on the end of this, stick it up in the air, and as the wind blows, it turns this, and you have changing magnetic field related to this, and you're producing a current. So that is a wind turbine power generator. If I take that same idea, stick it at the bottom of a dam and run water over it, or inside a river, something like that, that's a hydroelectric powered dam. Hydroelectric power plant. In the case of a coal burning power plant, it's the exact same idea. The difference is you take coal, set it on fire, put a pot of water over it, water boils, turns to steam. Steam rises, and you put that same device in there where you have a fan or some type of a turbine. So the turbine will turn due to the steam rising, and that will spin a coil of wire relationally to a magnetic field to induce the current as we saw earlier. So that's how you would produce it with a coal burning power plant. A nuclear plant actually works exactly the same way. The difference is instead of burning coal, you simply take nuclear rods. Nuclear radiation just means that something radiates out from the nucleus, and so energy of some form is coming out. A few different ways that can happen, but certain types of this radiation that comes from the nucleus, the energy that comes out can be absorbed by water. So the water boils, turns to steam, steam rises, turns the turbine, the exact same method. So all the methods of power generation that we have of generating electricity is done through this same idea with the exception of solar. So that's it for this week, and just let your TA know if you have any questions.